Very good afternoon to everybody. My name is Dhirendra Tripathi. I am working as a process engineer at ANFF node. And today I will be discussing about optimizing the MEMS spectrometer, their designs, fabrications, process, and the material engineering, which we have done over the several years. So outline will be just discussing about the designs which we have progressed over the years, and some of the fabrication challenges which we have solved recently, and what we have learned, the lessons through all the changes which we have brought, and the knowledge of the materials and the MEMS designs which we have gathered over the years, and how that can be applied over the several other fields which are very relevant for the MEMS and other photonics community. The ANFF is having a MEMS sensor development in two major areas: MEMS spectrometers and MEMS cantilever-based sensors. So earlier, yesterday, you have seen one of the presentation which was based on the MEMS cantilever-based sensors. And today I'm presenting the MEMS spectrometer. And morning, one of the colleague Nima has presented our work done in the focal plane array. So combining the focal plane array with MEMS spectrometer, we are moving towards developing an in-house capability of developing adaptive focal plane arrays. So our MEMS spectrometer technology has evolved over several years, and now it is covering a wide range of wavelength operations: visible, near, shortwave, infrared, midwave infrared, long wave, and terahertz as well. And one of the motivations, recent motivations for us to evolve our devices was the multispectral imaging and hyperspectral imaging. Now we know that the drone has caused a lot of revolutions in the imaging area, and the drone-mounted cameras has become more common for getting a quick image of any field or any area which we want to observe. However, the multispectral and hyperspectral IR imaging is still expensive. The part of the reason is that the development has yet to be done for the cheap cameras. And why we are looking for the hyperspectral imaging and multispectral imagings is that these images, through their IR signature, they are able to gather a lot of information which is generally not available in the visible light images. We can diagnose their chemical properties, their current state of like soil moistures, and in defense and security, we can differentiate between the artificial and the synthetic and the natural material, and can identify whether it is camouflaged or not. So all this information is generally hidden in the spectral of a material, and that can be exploited using the multi-hyperspectral IR imaging. I'm showing you one example of one leaf which have been hyperspectral imaged, and as you can see here, there's a spatial dimension of the leaf which is giving the size of the leaf, and the spectral dimension is giving the information about the IR spectra of the leaf. That essentially carries the information about the type of variety of the leaf, and also the moisture it may contain, and other properties which nowadays agronomists are using, agriculture scientists are using for developing smart farming models. Okay. Now, we at the ANFF node are looking towards miniaturizing the hyperspectral cameras. So earlier, the hyperspectral cameras, the last generations were based on big bulky optical optics, which were very expensive. It has to be mounted on the planes or some very heavy vehicles, and so they could not be employed on the field so easily. And now with the MEMS space, we are trying to reduce the size, weight, and the power consumed by the devices. And as we know that MEMS has its own fundamental property, that it is mechanically very robust. It can be produced in a large quantity, so that can offset the cost which is associated with the making devices. And MEMS are very fast switching, so they can generate a quick spectral information of the scene which is being absorbed. A simple fundamental principle on which our MEMS spectrometer works are that we have two moving distributed bag reflectors, and once the broadband light falls on these distributed reflectors, the distance between this reflector decides that what wavelength range will be passed through them. So essentially, this spectrometers works as a passband filters. And as we change the distance, the type of spectra changes. However, this also creates another challenge, which is that if the distance between this top mirror and the bottom mirror is not essentially flat, then the variation in the distance between one corner to another corner of the top mirror or bottom mirror can create a variation in the wavelength across the pixel length, and that creates the problem with the imaging. We don't want them to have this kind of variation in the flatness. So this is very early design where we just started working with the spectrometers. It was based on simple X membrane. The optical area was just 90 by 100 micron. So it was just like more a prototype, sensing the IR sensing. And we have not, then we evolved this design to another design, which was based on the fixed beam actuators that allows us to have little more flatter membranes and gave us more actuation, what you call electrostatic tuning range, that allows us to capture a wide range of wavelength in a single tuning. However, the problem with these devices were there that once we try to increase the area, effective optical area of the device, the stress which is inbuilt in the materials which were used in the mirrors was causing the buckling of the mirrors, and also this the supporting structure was, as you can see in this green image, was also getting stressed. And when we try to increase it further, we were finding that supporting structure was not strong enough to hold these large mirrors, and they were pulling off from the substrate. So it was leading to the failure of the devices. And we also found that in these devices, there is a lot of area which is not optically active. As you can see, only the mirror, which is hexaoctagonal, possibly, that is optically active, but rest of the area is not optically active. So here, in parallel to the development which we were doing in the MEMS, the focal plane array community were coming with the newer developments. As we see one of the example of a simple focal plane array, they are becoming much more denser and smaller in the size. And if we have to build any adaptive focal plane array on top of them, then it is essentially required that our MEMS optical area should be enough to cover the entire focal plane array. So we wanted to move to the imaging because that is the big market. So we decided when we need to make drastic changes in our designs on fabrication process. So we came up with a design where we had a mirror which is a square mirror sitting in the center of a suspended membrane. This suspended membrane was supported all around with a sacrificial layer or on the substrate. That allows us to have a big square optical mirror, which can be fine-tuned to the size of the focal plane array which we are trying to combine with. And that allows us to also deal with the different kind of materials. And we relied on the tuning of the intrinsic stress of the materials to keep this membrane flat. And one of the things which has helped us a lot, thanks to ANFF YouTube node, is their tool, Centec PCVD tool, which they have donated kindly to us. That allowed us to tune properties of silicon-based material significantly. And the uniformity of the depositions for over 4-inch area, that was very much needed for us to make large area devices. So one of the projects which we did with our industry partner has a very specific requirement of multi-millimeter area flatness. As you can see here, on the 5-millimeter area, we developed a device for them which was having just 40 nanometer of variation, which was a very significant achievement for us. Going by that, we also developed our Inhome devices, which were single membrane-based single silicon membrane-based MEMS spectrometer. And as you can see, they are able to tune from entire shortwave spectra with 180 nanometer of FWHM. However, when we were trying to move to the long wave devices, we had a problem because long wave material is generally very rare. We have germanium, which is a kind of semiconducting material. And when we were putting the germanium in the scene and we were trying to actuate it, the conductive nature of the germanium was making the optical area also buckling around along with the actuation voltage. So that caused a problem with the spectra. We could not get the spectral tuning with a symmetric wavelength spectra. So because of this spectral broadening, we decided we need to change something more in our designs in the process, so that this process should be compatible for any other for long wave or any other kind of wavelength which we are targeting to. So what we decided, we are going to make the optical and the structural material different, but we are going to keep the MEMS fundamental design same, because that gives us opportunity to make the square devices or rectangular based on what FPA we are targeting to. And we developed an entire range of depositions, depositions materials and their stress properties for in these coming 2 years to develop something, a different kind of design. Here I show you a 3D model of the 4x4 MEMS die, which we are fabricating nowadays for the short wave, long wave, or any kind of material. So as you can see here, we have the mirror material, which can be based on anything: silicon air, germanium, silicon dioxide, or silicon nitride, any combination which suit to the wavelength range which we are trying to operate. However, the entire actuation structure is holded by the silicon nitride, which is a non-conductive material, very sturdy, and that these kind of changes allows us to generate the devices which were exceptionally flat, optically flat, and they were performing very well tuning, as you can see here in shortwave spectra. We are tuned from 2500 to 1800 with 38 nanometer of FWHM, and these changes on the devices was just not that we were making the devices, we were actually creating a culture of material, we were creating a culture of creating the designs where we could use our materials to create any exotic MEMS. Suppose we want to make a mirror made of metamaterials, we can combine the same technologies and make something which is operating in the terahertz. And all these materials, information which we have generated for silicon, silicon oxide, silicon nitride, germanium, has benefited so many industries. And many researchers in the ANFF and other university have also benefited with our research which has developed in this area. With this, I just want to acknowledge the industry partners and ANFF and government partners who have helped us to develop this entire program. And I'm open for any question. Thank you.
Thank you very much for your insights. They were fascinating, and I think many people here were taking very close note on what you were sharing. Unfortunately, to make certain that we can keep to time, we will need to move on to the next speaker, but I would invite anyone who does have any questions, thoughts, or would like to share some of their own insights to reach out to the author and make sure he understands and get to the bottom of where you can both collaborate together.